Hey, welcome back. Today we're going to be talking about how to take the derivative or integrate two-dimensional position, velocity, or acceleration sine or cosine equations / functions. This is for AP Physics C mechanics students or similar classes if you're a university student. And let's go ahead and get to it. So this problem says a particle moves in the x and the y plane with coordinates given by, and then we have two equations here. And we're told what a is equal to and what omega is equal to for these two equations. So it's really the same wave function, but it's broken up into the x and the y coordinates. Now I want to start with, what do we have? Do we have position, velocity, or acceleration? What do you think? Well, we've got position, and what are we looking for? So position, because we have these x and y values, what are we looking for? Well, we're looking for acceleration. So we want to go from position to velocity, and velocity to acceleration. So effectively, this is a two-step process, right? And because we're going from position to velocity, that would be a derivative, and you take the derivative of the velocity, and that will get you the acceleration. We have to do this for both the x and the y, and then come up with a conclusion at the end about how we are going to relate those functions together in something that summarizes all of the above. Okay, well, we know that velocity, in terms of comparing velocity and position, we know that velocity, it's the derivative of x with respect to time. Now, it's really crucial that we know that you have access to equations here, so you don't have to memorize this. It's really crucial that you know that you can take a look at this. Notice that we're starting with a cosine function. This cosine function is right here in terms of the rule. So this is on your equation sheets. I can't tell you how important it is to take a look at this stuff on your equation sheet. On the back side, there are reminders about most of the calculus that you're going to need to know how to do. So if you take the derivative of a cosine function, notice that you're going to end up with the negative of a sine function in general. It's actually a useful idea to get into thinking about why that is. But notice what we're going to do is we're going to take the coefficient that we have out here. It'll be dragged out in front. So this coefficient originally in front of the x gets dragged out in front of the remaining value here. So our original equation again is, here I'll write it here for reference, a cosine omega time. That's going to be this value. By the way, this is amplitude and this is angular speed. Or in some contexts, this is called angular velocity if you know a little more information about it. By the way, you can think of angular speed in this context as being like a value that changes in terms of radians per second. So if you have a greater value, then the function is going to change more quickly. So for instance, in this dummy set of equations I've set up just to demonstrate the idea, the blue function has a greater omega stand-in of 6, let's say. And you can think of it as the blue function is changing its direction more quickly than the red function is. If you take a look, the red function effectively would have a lower angular speed of a value of 3. Just to give you a visual idea of what we're talking about with angular speed, the a value out in front, amplitude, is just the distance from the function itself to the middle axis line. So a greater amplitude means a wider or fatter or higher wave, however you want to think of it. That's our function. Now if we take the derivative of that, we need to think about, all right, well, what's the coefficient that we're going to bring out in front? Well, the coefficient is going to be omega. We do have to make it negative as well. And we do still have the amplitude left over, and the cosine turns into a sine function, and we are left with what was originally in this sine function. In other words, and we are left with what was originally in the parentheses here of this cosine function. So we have to leave this here as well. So that's what we get. This is velocity in the x. We should label it as such. And what we can do is actually take it to the next level in terms of taking it one step further. So that's our velocity in the x. Let's do our acceleration in the x. If we do the derivative, again, same process, you are looking at this bottom left two equations over here. Now we're working with the original sine function, so that's going to bounce over to a cosine function, so I can go ahead and write that. And we still have the cosine of whatever's in the parentheses here. This is still going to remain right here, right? So we can include that. Notice we don't take the negative of what we had previously. It was previously negative, so we can just leave that negative derivative. This was our previous coefficient. We can leave that there, omega a. But notice that we had a omega in front of the t. We do have to account for that. This is going to be omega squared a now. And so we're left with this for our acceleration. This is for our velocity. This is dealing with the x-axis. Now let's go ahead and do a similar process with the y values. So if we take a look at our y equation right here, so I can rewrite it and say y is equal to a sine omega time. Now you should say something like dy dt is equal to v if you're going to write this up as a FRQ. If this is part of an FRQ problem, a lot of times the graders will want to know that if you take the derivative of a position function, you're going to end up with the velocity function. So let's continue. Looking at our rules in the bottom left down here, this is fundamentally a sine function right here, right? So we look at this rule right here. You take the derivative of a sine function and you end up with fundamentally a cosine value. So v in the y-axis is equal to, I said it was a cosine function. Remember, whatever's in the sine function originally, we can think of these as being in parentheses here. That ends up over here as well. That's not changing. And notice all we need to do here is take out that coefficient that was inside that sine function. So this is our coefficient. I'm talking about this omega here. It gets drawn out. And we can't forget the previous a as well. So that's what we have for our velocity. And let's do one more derivative here. So we're going to say, let's take that to the next level. Remember, this now fundamentally is a cosine function. So we want to take the derivative of a cosine function. You end up fundamentally with the sine function. So that's a pattern. And it is a pattern that you're going to leave whatever's in parentheses essentially here as well. In this case, you want to take the negative of the coefficient that we have inside there. So that's going to be a negative a omega squared is going to be our acceleration of the y. So these are two things here that we have now solved for. But if you take a look at the question that we have, it says, what is the magnitude of the particle's acceleration? It does not say in the x-axis or in the y-axis. What they mean is we need to do this in a two-dimensional sense. We need to combine. So if you had, let's say, one vector in the x and our y vector, how could you solve for the resultants? Well, you would just use the Pythagorean theorem, of course, right? And that's what we're going to do here. So we can say our Pythagorean theorem is just going to be a squared plus b squared is equal to c squared in general. All right, and so we could say, well, c squared in this case is equal to a squared plus b squared. And what do we even mean by that? Well, we mean this is our general acceleration equation. Squared is going to be equal to our acceleration of the x squared plus our acceleration of the y squared. Okay, now this is going to get a bit messy. Just hang in there and we'll see how it goes. We already can anticipate if we take the square root of this will be canceled. And we want to take the square root of whatever we have in here. Let's think about what we have. For our acceleration of the x, we've got minus, this is omega squared a cosine of omega t. Okay, that is quantity squared plus parentheses minus, and that is quantity squared, and this is all underneath a root symbol. Okay, I need to shift the screen to get a little more room here, and so we can think about this, and I'm just cleaning this up so it's clear that this squared function is on the outside of that parentheses right here. So we could say our acceleration function is this. So let's apply the squared function to each of these terms. And that's what we have. Notice that we can combine like terms here. So we can say this. And that means we can draw out this and make this omega squared a times this business that we have. Okay, and at this point you can plug in your numbers, or there may be something that you notice. If you happen to know that we have a trig identity right here, this whole thing actually reduces to 1. If you spot that, that makes the problem a lot faster. But you can still do it even if you don't spot that identity property right there of trig. So we're just going to speed this up and say, all right, well, if we call that 1, then we can say our A, our final answer, is going to be equal to omega squared times big A, our amplitude. So A is equal to, we said this was equal to 2.2 and this was equal to 3 radians per second right here. So if we do the math and round it off to 2 sig figs, you end up with 20 meters per second squared. That's going to be your answer. And that's how you approach one of these two-dimensional problems using sine and cosine functions. Doing derivatives and integrals are going to be very similar. I do want to emphasize, if you can do the derivative section, you can do the integral section. Take a look at this. Remember, these equations right here are on your equation sheet. That's crucial. So you don't have to have this memorized, although I will say if you do memorize them, it does speed up the process a bit. I also want to say you can do this. Even if you're new to calculus and somewhat new to physics, you can do this. It can be done. No worries. You've got this. In any case, I've done lessons on an entire year of physics, as well as many concepts for AP Physics E Mechanics. If you have any questions or comments down below, please let me know. And I hope you all have a great day. Take care.